professor at the Case Western Reserve University in Cleveland, United States. And he's an expert in unification and its implication for proton decay. This is what he's going to talk us about today.
Thank you so much, Herman. It is actually a great pleasure to be back to Valencia after 10 years. I have to say that you guys are lucky. This city is very beautiful and the whole country is so pretty that it's really great to live here, right? And then today I will talk about new physics and the unification forces, okay? And I will do the colloquium in this way. The first half is for students. The second half is for more senior people. And for experts, they can talk to me after the colloquium. And let me start to thank my collaborators from different countries that have been working with me in this particular area. Let me talk a little bit about the fundamental forces. No? We know that we have gravity, we have the electromagnetic force, we have the weak force, we have the strong force, and 5 years ago we discovered a new force, okay, which is the Higgs force. Then if you have, let's say, two quarks, they can interchange gravitons, they can interchange a photon or a gluon and a Higgs, and then in this way we could understand the interaction between matter, okay? We are lucky that now we have a new force in nature. Maybe soon the LHC will discover something more, no? Gravity can be described pretty well with GR, okay? So far you can do pretty well. And the standard model can do pretty well for the rest, okay? When I say pretty well, it's that you can explain most of the properties, okay? And it is easy to say that you can say that the theory of fundamental interaction today is just GR plus a standard model, okay? With these two theories together, you can do pretty well, okay? You can describe most of the properties that we see today, okay? This is what we see in nature, okay? Beautiful to see that the standard model of particle physics can do the job for form, okay? And you always can make a joke to gravity people that, you know, do particle physics, you do more than them. This is not true, okay? Now, the people for many years tried to study the unification forces. And the main idea behind that is that you try to build a theory which could be way simpler than the standard model and GR, and try to put everything together to see how you can simplify, okay? This is the key idea of unification, simplicity, okay? We don't know if this is true, but the people try for years, okay? Then one idea that has been in the market for a long time is the idea of grand unified theory. In that context, you can unify the electromagnetic, the weak, and the strong interactions, okay? I will discuss mainly these things. There are other ideas which are way more speculative, okay? For example, you can maybe understand the unification of gauge forces and the Higgs force in so-called gauge-Hughes unification scenarios. They don't work so well. People try. And of course, you heard that there is something called string theory, or SONSI. Sometimes, you know, people call this in different ways. That the main goal is to unify everything, okay? But these are really even way more speculative than grand unified theory, because at least for people working in particle physics, we understand pretty well the standard model of particle physics. We know how to use quantum field theory. And in grand unified theory, you face the issue that the theories are even simpler than the standard model, and you can use all the tools of quantum field theory to study all the predictions. Huh? But once you go beyond, in my opinion, it's quite complicated. That's why I will focus mainly on that. And I will try to explain all these properties. Huh? Now, let me start with the story about unification. No? In '74, before I was born, Georgi from Harvard Helen Quinn from Stanford and Steve Weinberg, at that time he was at Harvard, they wrote a very interesting paper where they basically did the following. No? Alpha 1, alpha 2, alpha 3, these are basically a parameter that tell you, it can give you idea how the matter, for example, feel a given interaction. Like alpha 3 tell you, for example, how the quarks they feel the strong interaction, how the gluons between each other feel the strong interaction. And alpha 2 and alpha 1 together, they can describe the weak and the electromagnetic interaction. No? And they did an interesting exercise that they studied the evolution of these couplings with the energy scale. Okay? And they found, that somehow they tried to get together. In 74, they didn't really knew these values here that you see. Okay? And then I will give all the credit to them. They saw something there that maybe these gauge couplings could, and some energy scale, have the same numerical value. Okay? And maybe you could say, maybe this is an accident, no? But this is a little bit profound, okay? Because today, for example, we know that below, let's say, the electroweak scale, we have the standard model that can describe physics very, very well. We have the Large Hadron Collider exploring this region of the parameter space, the TV scale, okay? And if this is true, at some energy scale, you can expect a new symmetry or a new theory that we call unified theory, because all these interactions behave in the same way. Okay? But the interesting part here is that for years and years, the experimentalists built many good experiments, and so far the best that we have is a Large Hadron Collider exploring the TV scale, and there is no really hope to build any collider that can prove a super high scale. Okay? And then the first thing that I want to say is that maybe this is very beautiful, but there is no way to know about this in a real experiment. Okay? Yes, because you cannot produce the new fields that maybe live in this grand unified theory at a high scale. Okay? But maybe this is true, okay? And we have to think about that. But keep in mind, it would be great if this, accidental, or if you can explain, unification, could be realized at the lower scale. And I will tell you why typically this is very, very hard. Okay? And this is a simple idea of grand unified theory from the bottom-up approach. You use the information that you have at low energy, you try to extrapolate your theory at higher scales, and maybe you try to learn what could happen. Okay? Now, what I will do in this colloquium is I will talk about different ideas for new physics and the unification. I will focus on the main scenario that is the high-scale unification, where you cannot really test this in a collider, but you have predictions that you can maybe look for. And I will try to tell you a different approach that tells you that maybe there is a way to unify a very low scale, and you maybe can hope to test this in colliders. Okay? That would be really fantastic. Okay? And I will talk about all the predictions in different scenarios. Okay? Now, this is the plan. Introduction for students. I will talk about grand unified theories. I will tell you how to unify, or how you should follow, which idea you should follow to unify the low scale. And I will give a summary, which is maybe you can keep after this talk. Introduction. Thanks to Glashow, Salan, and Steve Weinberg, we have this amazing theory for the so-called standard model to describe the electroweak, the electromagnetic, and the strong interaction. Okay? This is a renormalizable relativistic quantum field theory based on this group. SO3 for strong interaction, SO2, and U1 to describe the electroweak and the electromagnetic interaction. For each group, you have a gauge coupling. This alpha that I mentioned before is just G squared divided by 4 pi, just the same, just different way to write. And in this way, you can, if you study the values of these couplings associated to different interactions, you understand how matter feels the different interactions and so on. And in the standard model, we have the physical fields, the gluons for a strong interaction, a W and the C for the weak interaction, the photon for the electromagnetic interaction. Okay? We have quarks and leptons. Okay? They have different properties. The quarks, they feel the strong interaction. The leptons, they only feel the weak and the electromagnetic interaction, something. They have, in 2012, we were lucky because the LHC managed to discover the Brown-Engler-Higgs boson, and now we know that all these fields here, they have a spin 1, these fields, they have a spin 1/2, and this is the only one in the theory that has a spin 0. But what's always crucial in the theory, as I will explain later, no? The quarks, they have an interesting property, is that they have a quantum number that is called baryon number. They have baryon number 1/3. A proton is made of 3 quarks. The proton has baryon number 1. And the leptons, they have a different quantum number that is called lepton number. That is 1 for all the leptons. Okay? Now, the standard model has been doing pretty well for a long time. This is a plot from, pretty old plot from 1990, where the people compute the E plus E minus collision to mu plus mu minus. And you can see that if you try to match experimental prediction using only QED, you cannot do the job. But once you put the Z, you can actually explain very well the experiment in very, very high precision. Okay? Already, for a long time, we knew this sector of the standard model was doing very, very well. Then, this is why we call the standard model a theory of nature, no? This is a collection of many, many, many studies at the lab colliders. When you study many, many, many cross-sections, you do, again, the theoretical calculation, check the experiment, and you can see that you can be in agreement with most of this experiment very, very, very well. No? This is actually pretty impressive. The standard model is the best theory that we have in nature to explain many experiments with high precision. Okay? I just will give you one idea how well we know these things, like the mass of the Z. We know this in super high precision, the decays and so on. This is so good that it's hard to imagine that you can do better in any other theory. Okay? Now, for a long time, we knew that we could explain many properties in the standard model, but we had no idea how to explain the mass generation of the standard model. And the hypothesis was that you have this symmetry, and we use a spontaneous symmetry breaking, because this is the most predictive way to understand generation of masses. And this was postulate the so-called Brown-Engler-Higgs mechanism, where using this mechanism we used to assume that this symmetry, the electroweak symmetry, was broken to U1 electromagnetic, and this way explain why the W and the C were massive and the photon is massless as well. Okay? And as you probably, most of you know, this is the Nobel Prize of 2013. Okay? Now, thanks to this great experiment, the Large Hadron Collider, thanks to CMS and Atlas, now we know that the Higgs is a real thing. Okay? This is the plot where you discover the Higgs to gamma. And now we know this is the real thing. We know pretty well now the properties of the Higgs still. These are basically how the Higgs decay to 2 photons. Okay? If you compare to the prediction in the standard model and the prediction that the measure that you have in the experiment, you can see that in many of the channels, the Higgs can decay to all the gauge bosons. These are virtual W and Z, and some of the leptons and quarks. And today we know very well most of the properties, not all of them, but we know very well, no? But somehow this is actually closing a chapter in particle physics, okay? Basically, we can say the standard model Higgs, now we know that it's a real thing. It's a particle with a spin 0, and you have really the spontaneous breaking of the symmetry to generate masses. This is the fundamental way to understand the generation of masses in nature, okay? And it is important to say that the standard model provides a good explanation for most of the experimental results that we have in particle physics, okay? And then, this is the only thing that we know that is true today. The rest of all the ideas that you see in the market, they are just speculations, ideas, fantasies. Any idea, we have no idea, okay? The standard model of particle physics plus GR, in this you do very, very well, okay? Now, even if the people have been thinking for a long time, it's good to think hard again. Because, why again? Because now we know that the Higgs is there. Before we were not sure, maybe the symmetry was broken in a different way. But actually, the Higgs is a real thing, spontaneous symmetry breaking is playing a role in nature. And it's time to think even harder now, okay? Now, of course, you can think in different places. Paris is a good place to think, especially if the weather is good. I will just talk about some questions that you can ask, okay? One of the questions that you can ask is why the standard model interactions are so different. You have the strong, the weak, and the electromagnetic interaction, and they are very different. These values, the parameters, they actually have different values, and the matter field in different way these interactions. Huh? We have no idea. If you try to explain the masses for fermions, the electron mass is so tiny, and the quark masses, like the top mass, is so large that we have no idea. No? Today we know that the neutrino, for example, is massive. This is a good question to think about. The standard model doesn't provide the mechanism for that. This is a good thing to think about physics beyond the standard model. We know that we have 3 families of fermions, but we have no clue. Why is that? Today, after the Higgs discovered, this question is even more relevant because it used to be that we were allowed to put the 4 family in even properties, chiral families, but this today is not possible in any model of physics beyond the standard model because this will destroy the property of the Higgs boson. You cannot do that anymore. Then I will say this question is becoming even more interesting today. And the Higgs mass was discovered with mass of 125 GeV. We have no idea why is that. Nobody knows. Okay? This is a very interesting question. And if you go, of course, to cosmology, we know that there is cold dark matter in the universe. We think that there is cold dark matter in the universe. The standard model doesn't provide the mechanism for that. It would be nice to have. And at the same time, we call us matter. And since we don't see our antimatter guys around, it's important to understand why we are around and they are not around. And then typically, the standard model cannot really explain this big difference, okay? Now, I will focus in this colloquium mainly on this question here. Why the standard model interactions are so different, okay? The best way to explain that is using grand unified theory, okay? The first idea in the market to think about grand unified theory was actually pointed out by Yogesh Pati and Anandu Salam, the same Salam from the standard model, great physicists. Okay, they basically, according to Yogesh, he was ICDP in Trieste, bothering Salam. How is that possible? We have quarks and lepton. What is that? Why matter has to be different? Why they cannot be the same somehow? And they proposed the so-called idea of quark-lepton unification, which generically predicted a very interesting phenomenon. Is that I told you in the standard model quarks they have baryon number. This symmetry is actually accidental symmetry in the standard model. It's broken at the non-perturbative level, but it's basically a pretty good symmetry. And in the standard model, you know that the proton is actually stable because even the baryon number is broken in 3 units in the standard model. To get proton decay, you have to break in 1 unit. Therefore, this is a very hard prediction of the standard model of particle physics. The proton is stable, okay? Even at no perturbative level, okay? Because it's broken in 3 units, not in 1 unit. However, they say if the quarks and leptons are not so different, somehow they live together. The problem when you do that, you put quarks and leptons together in a, we say this in a in a box, on a multiplet, this symmetry barrier number is broken, because you cannot define that on the scale where you unify matter. And therefore, you should generically predict proton decay. Later, the details are different, depends which theory you write down. But this is the first idea that actually initiated the idea of unification, okay, in particle physics. And later in '74, George and Glashow, they proposed this amazing idea that the standard model gauge interaction could be unified in just one gauge group, SO5, okay? In the standard model, we have SO3, SO2, U1. Here you have just SO5. Very simple. Beautiful. Okay? Just simple. And then they have the answer to this question. Why the standard model and the interactions are so different? The answer is very simple. They say, don't worry. The strong, the weak, and the electromagnetic interactions are just different manifestations of the same fundamental interaction at the low energy. Then at low energy, you see that they have different values, or the matter feel the different interaction in a different way. But if you go to high energy, they will feel just one force. Okay? They will feel just one force. It's impossible to distinguish between them. Okay? Of course, we cannot go to super high energy, because when you do, you study this more in detail, you say, very beautiful, I can unify this in just one group. This is very, very simple. Okay? And we know that the energy scale where we can do well with the standard model is below around 100 GeV. But I told you that if generically you follow Pavel, as I will show you, you will get proton decay, and this symmetry cannot be realized at this energy scale, has to be realized at the super, super high scale. Okay? Which is very depressing. Okay? Because the idea is very, very beautiful. It's hard to imagine. I recommend any student to read this paper. It's a bit interesting, because they say that they are totally convinced this is the symmetry of the universe. No? But you know, the point is that the experimental result tells you that maybe it's true, but you have to realize this at the super high scale. Okay? And then this is just matching the idea, the result of the St. George, Ellen Quinn, and Weinberg, that they saw, very naive at that time, the unification of the super high scale. Okay? And then, of course, I am not allowed to give you details in a colloquium, but at least for, to give you a feeling, you just unify all the interactions in one gauge group. You will have only one gauge coupling in this case, and the quarks and leptons, they live together in two representations. But the important point is that you put quarks and leptons together, and they are at that scale where you have the symmetry, they are not different anymore. Okay? And again, when you do that, because you say it's very beautiful, I like to unify. When you do that, these symmetries of the standard model, the baryon and lepton number, they are broken explicitly, because you are forcing the quarks and leptons living together. They have different properties. Once you put together, they cannot share the same property. And then these baryon and lepton numbers are totally broken, okay, at the scale where you have the symmetry. Then this has, as I mentioned, huge implications. There are new fields in the theory. This is not relevant for this discussion, just mentioned. But the important thing is that you can avoid the decay of the proton. For example, the proton can decay to a positron and a pi zero, which gives you two photons. And then this idea was so impressive, still is very, very appealing, that since '74, the experimentalists, they got crazy and started to build detectors, and detectors, and detectors. This is one of the detectors. Okay, this is a well-known super Kamiokande detector, which has only 50,000 tons of water, very small, right? Has like 13,000 photomultipliers. You see, you can actually swim inside if you want. And what they do, they just wash the proton in water to see if they see a decay from the proton, okay? And they have been doing this for a long time, okay? And pretty much they have the best bounds that we have in particle physics. This is a list of channels huge amount of numbers. There are many, many collaborations, but I will just show you two. Okay, look, this channel is bound, the lifetime has to be above 10 to the 34 years. This one as well. And when you do take this into account, and you compute the proton lifetime in this grand unified theory, this tells you that the new gauge fields mediating proton decay or giving this process, they have to be supermassive, okay? And again, it's depressing, because you say, okay, beautiful, I can unify in SO5, great. SO5 gives me a prediction, a new prediction in nature, which is the proton decay. Very beautiful. But I don't see proton decay, and the theory has to be at a super high scale. Okay? Depressing. Or maybe nature is like that. We don't know. Okay? And this is what, for a long time, we call this, for more than 40 years, physics at the high scale. It's maybe like a dream, maybe? But somehow many people like that. Okay? This theory doesn't work very well, but you know, it's good enough. You can accommodate many things, many of the problems. For example, this is a prediction that I have when my students, Clara, that is here. You can actually write a theory that is totally realistic. You can explain, you can have a consistent relation for Fermi masses and everything, and you can compute the lifetime of the proton. And this is, for example, for the pi zero positron, you can actually do a very good calculation. You can use the super Kamiokande bounds, and you can see that if hyper Kamiokande can actually, this is the projection for hyper Kamiokande, which is the new generation beyond super K, you could see maybe a way to see if this theory is true. You could imagine that the hyper Kamiokande detector, you could see a signal. Okay? But again, even if you see proton decay, okay, you will make a celebration. In Japan, you will drink maybe a lot of sake, I don't know. But because it's a new phenomenon in nature, the proton will decay. This is pretty amazing. Okay? However, you cannot go beyond that. You cannot say this prediction corresponds to this very well-defined theory, because in reality, when you check that, is super high, super difficult to make a conclusion. You can say, you can maybe rule out a theory, you can be consistent, but the fact that we cannot have access to this super high scale, we cannot produce the fields that are mediating proton decay in a collider, we never can really test a grand unified theory. Okay? And then you live in a very funny scenario regarding unification. You know, we know that we have the standard model here, very large, low scale, no? Very beautiful theory. And I told you, proton stability, generically, will tell you that your unified theory doesn't matter how pretty it is, it doesn't matter if you had a coffee or a tea when you wrote the theory, has to live at the super high scale. Okay? And the large hadron collider can maybe prove this region here at the TV scale, but never can go there. And this is something that has been around for more than 40 years in particle physics. It's called the Great Desert Hypothesis. It's that you have two physical scales that are far each other, really far. And the only thing that tells you that this has to be like that is just the fact that the proton doesn't like to decay. Okay? Just doesn't like to decay. The bounds are pretty amazing. The best bounds that we have in particle physics. There is nothing that can prove a scale of 10 to the 15 GeV in high energy physics. Okay, this is the story about the ideas of grand unified theories and proton decay. But you know, we theoreticians, we get really, we like to play even more than that. And there are more ideas like supersymmetry. Okay? Supersymmetry that people like for many reasons. It's a very beautiful idea. But this game of meeting couplings here, in reality, 74 was okay because they didn't really know even the values of the gauge couplings. Today we know this doesn't really work. And when you use supersymmetry at the lower scale, you find something very interesting that you actually can meet these couplings at the super high scale, but again, super high scale. In reality, there are many, many details there, okay? But generically, it is fair to say that supersymmetry helps you to really do the job, okay? But again, it's super high scale. And of course, once you know supersymmetry, quantum field theory, and you already knew SO5, the same father of SO5 wrote the supersymmetric grand unified theory, okay? Just one step forward, okay? It's just putting supersymmetry in the game to help more to achieve unification in agreement with the experiments, but it's just the same idea with some extra flavors, okay? In that case, the situation is a bit different because maybe you can find the supersymmetry extension of the standard model at some low energy scale. We have no idea. This is just one speculation, just one more idea in the market. But it's interesting, it's a very appealing idea. But still, the unification will be at the super high scale. And if you check the theory carefully, supersymmetry theory, there are even more problems with baryon electron violation. The proton likes to decay faster, and it's actually very hard to accommodate the experimental bounds. Okay, but it's maybe appealing. It's a good idea that maybe if the LHC can discover supersymmetry, you could start thinking again. Okay, again. You have the standard model at the lower scale, okay? And you have, for more than 40 years, we had this beautiful idea of grand unified theory, where you have a new prediction in nature that say the proton is non-stable. You don't have to worry about that because 10 to the 34 years is fine for us, okay? We don't live so long, it is a pity. We'll be happy to change that, but it's impossible, right? Again, if this idea is true, again, we expect this unification at the high scale, which again is maybe interesting, but we never will be able to test this in any real experiment. And you can write beautiful theory based on SO5, SO10. If you like group theory, just play games and build more and more interesting theory. But SO5 has all the properties. It's the simplest thing that you can build, and in this way you understand unification of weak and strong interaction, okay? But again, this is super high scale, okay? Very pretty. Again, if you go to string theory, anything like that, they're talking about Planck scale, okay? That is again very pretty, but we never will know about this, okay? We never can build any experiment to test this, okay? Even if these ideas are very beautiful, very appealing, of course it's important to understand and to think about that. But the real fact is that we cannot test these things, okay? Now, let's assume that maybe this story is not true, okay? It's so beautiful that it will be great if you have unification at the scale that is maybe not too far from the, let's say, the Large Hadron Collider, or maybe the next collider, or the next collider, we don't know, okay? Suppose that you want to do that, and you say, okay, I don't really want to think about super high scale because I can live 100 years. In my lifetime, never will be able to know if this can be tested. Then you have to change the game, right? You want to unify, maybe understand the unification on the lower scale. How to do that? Well, this is something that I started to think about for a while with my collaborator Mark Weiss from Caltech in California, is that we say, okay, maybe this is possible, but of course, the proton has to be stable, because the proton is the guy that drives you crazy in this story, okay? You can do all the mathematics that you want, a very beautiful group theory and field theory, but the proton doesn't like to decay. It's just a fact, okay? You know, Feynman used to say, doesn't matter how smart you are, how nice you are, if the experiment says you are wrong, okay? Here, you don't know if you're wrong, because we don't know if the proton will decay, but it's good to think about, it's just even a simple question. Can you write a theory where the proton is stable at any level of perturbation theory? You know, if this is true, maybe this high scale, you don't have to have unification, the super high scale. Maybe you can unify scales that are maybe not so far from future experiments. Okay? But the proton has to be stable. This is the key point. Okay? And this idea is actually related to something different. In the standard model, we understand mass generations doing spontaneous symmetry breaking. Here, I told you that in grand unified theory, the baryon number is broken when you unify matter, but this breaking of the symmetry is explicit, it's by hand, when you force them to live together. You know, you take two people, sometimes they don't like to live together, okay? Even by law. They don't want. It's just a fact, you know, it's okay. You can move to Madrid, you live here, but they don't like to live in Valencia at the same time. This happens, right? Very often. Maybe the quarks and leptons don't like to live together, and maybe the proton has this key information, okay? And what you have to do in this case is to understand the spontaneous breaking of baryon number, not the explicit violation of baryon number. An idea, this idea was hidden in a paper that has like 20 citations. You know, the Georgi Glashow model has like 5,000, I don't know how many thousands of citations. This idea of maybe thinking about baryon number as, we call this local symmetry, was hidden in a paper by a great physicist, Brian Pice. He was a professor at IIS in Princeton together with Albert Einstein. And he just wrote a very short paper that say, oh, maybe, you know, baryon number is not a global symmetry, it's a local symmetry. And he just was happy to say that. He didn't develop anything. And this paper has like 20 citations. Nobody cared about this paper. Most of the citations are from me. But I'm happy about that because, you know, if you try the same stuff all the time, you are following just the same stuff. You go to the same restaurant to eat the same paella all the time, the same stuff, it's boring. You just have to go to, you know, maybe there's some tapas that you can eat that are better. Maybe they are not good, but you have to try. If you don't try, you don't know, okay? And this amazing physicist actually did a lot of things in QCD, a lot of things. He just said, you know, maybe baryon number is a local symmetry and you can understand in this way. Well, you will be surprised, there are only a few papers in the market. Everybody knows this, okay? In the field of high energy physics, okay? Let me explain you how you could maybe do that. Very simple ideas, okay? I apologize, I try to be not very technical. And the idea is very simple. You just take the standard model and look, this is very similar to, we call this hyperchar. We say this is now a local symmetry. I can do the same for lepton number, but I don't really have time to talk about that. You can ask me maybe later. Just think about just baryon number because it's actually the most important for proton decay. Again, you want to understand why proton is stable. If you manage to say that proton is stable, you don't have to live so far away, okay, from the lowest scale. Then I remind you the quarks, they have baryon number 1/3, the leptons 1, okay? And then you say, okay, very nice. I want to do the same thing that we do in the standard model. It's called spontaneous symmetry breaking, okay? We know, after the Higgs score, we know that this is playing a role in nature. It's a fundamental thing in nature, okay? Then let's follow that, because, you know, we know about this. Now, it's still not so easy because baryon number is a tricky symmetry. It's something that is called no anomaly free. For no expert, this means that, very nice, if you want to study the spontaneous breaking of symmetry, you have to make sure that this symmetry is good, also on the quantum level, before you break spontaneously. Because if it is broken at the quantum level, you have no idea what you're doing. Okay? This is something that is called anomaly. You have this funny graph and 3 gauge bosons associated to baryon number, and inside you have fermions inside. In this case, only the quarks, because the quarks are the only ones that they have baryon number. And you have to check all this graph and make sure that somehow they are 0. If no, it doesn't make sense to understand spontaneous symmetry breaking. In the standard model is so impressive that when you write all the the multiply for quarks and leptons and use all the quantum numbers, all these graphs are zero automatically. This is so magic. That's why it's called the standard model of particle physics. Well, if you check that, you realize that the situation is not really so bad. You realize that there are only two anomalies. Okay? I don't want to be technical, but basically there are only two types of graph that are not zero. And you say, oh, doesn't look so hard. Okay? You do this before lunch, go for lunch, come back, the lunch is good, you keep going, right? The food here is good, then you're fine. And then you check and you say, okay, maybe I can do a job. I can write a theory for baryon number, and this symmetry is anomaly free, and then I can understand the spontaneous breaking. I break and see what happens. I cannot give you the whole details, but believe me, we try everything possible, everything human being that we try, and the LHC did kill two possibilities. I mentioned you can have families that are similar to families that we have in the standard model. You can have something that is called Berthollet fermions. It's something that doesn't care too much about chirality, And then, before I give you details, let me give you the main conclusions of this exercise. You actually can show that you can have the spontaneous breaking of this symmetry at the lowest scale. You actually can do that in agreement with cosmology and any particle physics experiment. You predict a new gauge boson. It's like the photon, but it's massive, or couples only to quarks, which has very interesting properties. You have a new, like a Higgs boson with funny property we call baryony, because it has to do with the spontaneous breaking of baryon number. You find a dark matter candidate here. We were not looking for any dark matter candidate because I never told you anything about dark matter here, right? Told you just the proton is a troublemaker, and you want to understand the stability of the proton. You can show that you can actually explain even the baryon symmetry in the universe. And, as I told you, the key point is that if the proton is stable, you can start dreaming about unification at the lowest scale. Okay? Because again, I told you all these ideas of Georgi glaciers are very beautiful, but they can be only realized at the super high scale because the proton is not stable. But here, if the proton is stable, again, you start dreaming about changing the game. Okay? Okay, this is like the simplest model that maybe for some of you is really complicated. But not really. There are like only three fields, fermionic fields, and the Berthollet partner of these guys. But it's not even relevant for this discussion. Don't even look at this. The only thing that I want you to look is that these are the baryon number of these fields. And when I check this anomaly, this graph with three gauge bosons and all the fermions inside the loop, I want to cancel that and make the theory anomaly free, means that the quantum level is not broken, and I want to understand the spontaneous breaking. I find a funny conclusion is that the difference of this baryon number is -3. And this is interesting because I told you in the standard model of particle physics, baryon number is broken in 3 units. The proton is stable because the proton can decay only if you break baryon number in 1 unit. You can think about that. The proton can decay to a photon and a positron. The photon doesn't have baryon number, the positron doesn't have baryon number, the proton has baryon number 1. Okay? Then, of course, these new fields, you have to give mass to these fields because they have, for example, electric charge. And we have experimental bound from collider physics. We cannot have a live field with electric charge. Okay? Then if they have electric charge, they have to get mass. But they cannot get mass from the standard model Higgs because you destroy the standard model Higgs property. Then you have to introduce a new Higgs to break the symmetry and give mass to the new fermions, okay? And you will tell, okay, this is just a game, you just put a Higgs and you're done, huh? Well, it's actually not like that. The funny thing is that you find that this Higgs is forced to have a baryon number which is -3, okay? If you want to really generate masses, because the difference of the baryon number of these fermions are constrained by this cancellation of anomalies. Then, if you have that, this means that you can break this symmetry, but only in 3 units. This means that the proton is totally stable. There's no way to generate proton decay here, even if you have the spontaneous breaking barrier number. And I told you, you don't need to assume this tensor because proton is stable. Now, you don't have to worry about somebody that is far away from you. Just, you can start thinking that this can happen in any scale because the proton doesn't decay in this theory. And I have to say, this is a very simple question. Can I write a theory to explain the stability of the proton, assuming that it doesn't decay? Well, this is the way. Using the recipe of the standard model, using a spontaneous symmetry breaking. Of course, you can say you assume it doesn't decay. This doesn't make sense. Right? You have to explain things. Okay? And this is why I told you, if you have a spontaneous breaking of barrier number, the Templer theory tells you that the proton is stable, and therefore this breaking can happen at any scale, doesn't need to be at the super high scale. Okay? And then you don't need to have these 2 scales far away. And maybe, if this happens at the low scale here, you can test at the Large Hadron Collider, for example. Okay? Maybe. Now you keep going. And I told you, just do this and say, oh, great, the proton is stable in the theory. Is there something more? Yeah. You find that there is a dark matter candidate for free. You didn't look here for any dark matter. You find the gauge boson associated to this spontaneous breaking, and other things I don't want to bother you. But the funny thing is that here you find that all the signals that you could imagine in a collider has to do with barrier number and dark matter. You get dark matter everywhere. Okay? And this is interesting because maybe you can look for 2 things, for the spontaneous breaking and the barrier number. And now, let me tell you, you can ask me, okay, the Large Hadron Collider started to look for that? Actually, yes, for a while. They didn't have maybe the same motivation. They didn't care about proton decay or anything like that. But yeah, you can see the Large Hadron Collider put now much better bounds on the coupling of this gauge boson that has information how barrier number was broken. And this is the mass of this gauge boson. But the interesting thing here is that the bounds that they have, they are not so strong. This means that this is, even if this is happening at the lower scale, this doesn't need to be like a marginal theory where you have to kill couplings and do gymnastics to satisfy experimental bounds. No, you can actually satisfy all the bounds very easily, okay? And the funny thing is that they see even a very small excess there, but this is a joke, okay? Don't write a paper about that, please. Okay? People write paper for less, but don't do this, please. Then, what about dark matter? You know, I guess there are people here working on dark matter, also looking for dark matter in experiments. This dark matter candidate is very simple. Just did a fermion that coupled to this gauge boson associated to barrier number. And you can compute the Rayleigh density of that. You can check all the bounds that you have for dielet detection experiments. And you can see easily you can actually satisfy the experimental bounds in a nice way. Here you don't need to assume any, again, very peculiar scenario to explain the Rayleigh density of dark matter in the universe. And this is always welcome, but again, I didn't think about any dark matter candidate from the beginning. I was looking for something different. This is like a bonus that you get from the theory. Okay? And now, I told you that I can break this symmetry. I get the proton stability, have explanation dynamically to explain the proton stability. But you can tell me, this is very nice, but you know, you can do this at the Gatter scale, as George Glass showed, and we never will know about this, right? You can do this at any scale. A priori, you could do that, and the LHC, for example, never will see that, okay? But the fact that there is a dark matter candidate in a theory, you should be a little bit more careful, because there is a limit on the Rayleigh density of dark matter from cosmology, which is actually pretty impressive, okay? You could say this is even high precision, okay? I didn't write down the error, but this is actually pretty amazing how well we know the bounds on the Rayleigh density for a dark matter, cold dark matter candidate, okay? Then if you check this exercise, you'll find that this new gauge boson associated to the breaking of the symmetry, if you want to avoid, or we say sometimes overclose the universe, has to be below some 30 TeV. This is like, and this is good news because, you know, you smile here. I mean, you can smile when I tell you the proton is stable, you have a theory for that. Why you have to smile? Because, you know, the gamma scale I was talking about is 10 to the 15 GeV. This is just some TeV. Means that this symmetry has to be broken at the lower scale. Okay? Has to be. If you know, I am in trouble with cosmology. In the simple theory. Then you get something interesting. If this has to be broken at the lower scale, then collider experiments could hope to look for that, and maybe they find something. Because you have a very strong motivation from proton stability and cosmology here to look for that. Okay? If this theory is true, of course. Okay? You can ask me, often people ask me a very exotic process, I will skip that. And the important thing here is, again, the proton. The theory predicts that the proton is stable. This is a very simple question that anybody can ask. Any children from, well, maybe, okay, depends which is the kindergarten, but I guess, let's say high school, they can ask you, is the proton stable or not? Okay? Because the neutron decays, no? But the proton doesn't like to decay. Okay? And I told you, the whole story started that Georgia and Glashow wanted to understand the unification of forces, and they had this amazing prediction that the proton has to decay. But here I told you, this theory, where you understand the spontaneous breaking of baryon number, tells you that the proton has to be stable. Then, as I told you already, you start dreaming about unification here. Because this, you know, these lines that they were meeting at some high scale, this was consistent because the proton decay bounds are too hard. But now the proton is stable, maybe this meeting can change. And I can do this at the scale, but maybe the Large Hadron Collider or the next collider could test that, okay? Okay, then this is why I say, what about the unification gauge forces, okay? In this new type of theories, okay? Well, you can play many games here. Okay? You can play many games. The proton is stable. You don't care about the proton anymore. But you can do the same analysis that this guy did in 74. Okay? And try to see different scenarios. Here I show one, for example, that the unification is at 10 to the 4 TeV. This is, the LHC cannot see that. If you can go beyond that. The only thing that you have to do is you can have new copies of his fields, and you can change the evolution of the couplings, and maybe you can make a meeting at TeV. And this is okay, because again, there is no problem in cosmology, the proton is stable, this is possible, okay? But this is just like a naive exercise to show to the people that this is possible. You have to do better than that, because once you know that Georgi Glashow can do the job, you should do more than that. I have 5 minutes. Oh yeah, I'm fine. Good. Okay, and then again about it, you know, I am already happy enough to be able to say to you, you can write a theory where the spontaneous breaking bar number can explain the stability of the proton. There is a strong connection to cosmology. Cosmology tell me, be careful, you have to break this at the lowest scale if you don't want to overclose the universe, if you don't want to have too much dark matter. But, of course, you want to go back and try to reproduce the same thing that Georgi Glashow did. Okay? But I told you, sometimes people don't like to live together. In the usual grand unified theory, again, now you want to say, okay, in the usual scenario, I have S of phi, that never will know about this because the scale is too high. Never will know about this. There is no way to know about this. But it's very pretty. just SU5. Okay? And then I told you, this is like the theory that you have to have, let's say, the TV scale here. And it will be nice to unify that in a very simple group. Okay? I personally struggle like crazy thinking about it. You know, I guess I hope to find something better. What I will show you, I'm still not happy about, but you know, this is how you do science. You try. Okay? And then the key idea is actually pretty simple. The quarks, they feel the strong interaction and they have barrier number. Then it's natural to assume, okay, this is QCD and this is the barrier number. It's natural to assume that you can unify these two guys in SU4, in a new symmetry that's called SU4 color. Okay? Because they have, only the quarks they have this property. The leptons, they don't have barrier number and they don't feel the strong interaction. You cannot do that. Okay? This means that you have to unify the quarks of the standard model in this Berthollet fermions that I mentioned. Okay? And then you could imagine that you could have SU4 color, SU2 left, U1 hypercharge. The start. Okay? You unify strong interaction with barrier number. Because barrier number is a local symmetry, it's like a new fundamental interaction. Okay? And then you can try more, you can try harder. And the best thing that I found so far is that you can unify everything in SU4 cube. Okay? Instead of having SU5, that is very simple, very nice, and so on, the best so far that I found is this is the previous theory that you can break to something that is very well known through unification with barrier number. And when you break, you get this theory dimension that has to live at the TV scale. Okay? But maybe you don't like this theory. I don't even care about this particular example. I think the idea is so generic that anybody can take this idea and try to build something better. Maybe string theory is true, I don't know. And they can have embedding a more fundamental theory together with gravity. I don't even, you know, this is just a possibility. But I find this so appealing that I can explain the proton stability and cosmology tell me that I have to do at the low scale. And means that the collider people can actually look for that. Okay? Then the low scale unification again means that if you don't try what I said, I am afraid that the only way to explain the proton stability in a fundamental way is this way. I don't see a different way. But again, if you want to unify and change the rules of unification forces at the low scale, again, the proton has to be stable. Of course, you have to do this at the low scale. And you suffer because you don't have SU5 that is so pretty and so simple. You have to find a unified theory, if there is a unified theory like that, which is more involved, okay? But the idea, again, is very simple. Proton stability, and then you can go to the lower scale, okay? Then, in this way, I will summarize. For people that are no experts, for students, you don't have to remember any of these things. I only want you to tell you a few things. I told you that in the using the usual idea of grand unified theory, which are very, very, very appealing, you can understand the unification of the strong, weak, and the electromagnetic interaction. But this happens at the very high scale, and maybe you can see proton decay one day, maybe. But you never can make a test of this idea, never. Because we never can have access to this scale, direct access, okay? And I told you there is a different way. If you write a theory for a spontaneous breaking of barrier number, means that the barrier number has to be a local symmetry. You do a spontaneous symmetry breaking of that. Here you find that the proton is stable, then you can change all the rules of the game, okay? Then, to finish, there are two pictures that you have to use, okay? Maybe our understanding of fundamental forces or the unification forcing is like that. You know, this weird thing that you have two scales that are far away from each other. Or maybe it's something like that. You don't need that. The baryon number is a fundamental symmetry in nature. It's spontaneously broken the low scale, and things can be different. Okay? Muchas gracias.
So thank you very much for this nice overview. And now we have time for questions.
I apologize if I was maybe a bit too technical sometimes.
Could you comment a bit on the baryon asymmetry?
Okay. I don't have a slide here, but this is actually a very, very good question. When I started thinking about that, the people told me that I was dreaming because I never will be able to explain the baryon asymmetry because they are the so-called Sakharov condition. One of the Sakharov conditions is that you have to break baryon number. And here I am very radical. I even want to break at the very low scale. And the experiment allowed me to do that. However, what happens is that what I did was, there is a very well standard analysis is that you take the whole standard model, you assign a chemical potential to all the fields in the theory, and you do the thermal equilibrium equation, you solve for that, and you find that the usual thing is that they are a Falun process that they convert any B minus L asymmetry and generate a baryon symmetry. Here, what happens is that we managed to find that if the symmetry is broken at the very low scale, the Falun conditions are different, and I can write down that the baryon asymmetry is a linear combination of the B minus L asymmetry plus a asymmetry in the dark matter set. Then you could have something that is called asymmetric dark matter. That you have a relation between asymmetry in the dark matter set connected to the baryon asymmetry. Or if there is no this asymmetry, I will have, you find that the sphalons, they do the sensing, but the coefficient that we call the conversion factor is a little bit larger. But you can find a consistent relation between baryon asymmetry, B minus L asymmetry, and dark matter asymmetry without having any fine-tuning in any chemical potential in the theory. And this is how it works. Without giving any major detail, you have to think that this is maybe a box. And this box has two parts. One is these new fields that are there for anomaly cancellation and the standard model here. And there is a baryon number violation in the standard model and baryon number violation in this new sector. But the total baryon number is conserved. And this is a consistent way to see why in our sector we see a baryon asymmetry.
More questions?
The fundamental difference between your theory and every other theory is that the proton has to be exactly stable, right? So we have super K that says 10 to the 34 years, hyper K is probably 10 to the 35. How much larger would you have to make that experiment if you want to really answer the question whether it's stable or just long-lived?
Before I was born, they started to think about building these detectors, okay? Mm-hmm. Then the honest answer is maybe the usual idea of unified theories are true. But in reality, I spent a lot of time working on grand unified theory and proton decay, and you try very hard. And the honest answer is you never can make a very hard prediction for proton decay lifetime. Then nobody knows. If the proton is not stable, nobody really knows. You read in many places that will decay tomorrow, and you will say tomorrow because the theory, supersymmetry or any theory that somebody said that's beautiful, predict 10 to the 34.1. But this is, nobody really knows. When you really do the whole calculation using chiral perturbation theory or all the matrix elements, and you do the base calculation for the Gatt scale, it's depressing, it's very hard. Nobody knows. And the other possibility is that this theory says stable. That means that it's good as super K so neutrino oscillations, because if this is true, better not to have so many photon multipliers to look for proton decay. But they did a lot of science with neutrino physics, which was pretty amazing.
Yeah. So if I want to scale up, I want to go to really answering the question, is it stable or just long-lived? I guess if if the gut scale approaches the tongue scale, at some point I've become convinced that it can't be
It's more simple than that. If you find at the collider these gauge bosons and so on, you discover all this field and you realize that the baryon number was broken in 3 units, you're done. Because the proton never will decay. Of course, this is the first answer that you can say. And this will give you a hint, okay, looks like doesn't want to decay. This is the best thing that you can do. Discover these at the colliders and make sure that you understand that it's broken in 3 units, the baryon number. That means that proton, in this context, never decay. But it's hard to go beyond that.
And that will happen, probably not at the LHC.
We don't know.
We can't. We have
Depends of the mass. Depends on the mass of this. I am not able to predict. I only able to use cosmology to put the upper bound on that.
Okay.
It's very hard.
You can have tritium decay.
Yeah. Okay. Thank you for asking this question. This is one slide I didn't show. Thank you for asking this. Now I can go back and show you that. Yeah. This is the tritium decay. You see, you have to be careful because the tritium is stable. Okay. But the point is that if you check which operator gives you tritium decay, it's dimension 19. Then even if lambda is electroweak, this is 10 to the 100 years, then you're fine. You are not in trouble with any delta V equal 3 process. You are safe. You are lucky because this is a really good question. You do this, you will be in trouble in tritium decay. The theory tells you that it's highly, highly suppressed, and you have no issue in that.
In this unification, you used to have leptoquarks.
In the usual one or the new one?
The usual you have.
Yeah.
What about unification?
No, because a lepton-quark is defined as a field that couples the quarks and leptons. Here, you don't unify quarks and leptons. You unify quarks with this new stuff, okay? And then the new fields couple only to quarks and the new Bertholli stuff. They are no Bertholli. If no, again, you go back to proton decay.
Last question? No one? Something in the order of 30 TeV would be a motivation for a high energy LHC?
Look, I want to think about LHC because I don't know if I will be alive for the new collider. Then I want to make, people write papers about the 100 TeV. I think this is very important to support the community. So personally, I don't know if I can live 85, 95. I want to make sure that I want to think about LHC for a moment. But of course, you can use that as motivation. It's very simple. You can say to the people, a simple theory that predicts the stability of the proton, which is, this is like Wikipedia comment, right? It tells you that if, in a consistent way that the scale put in cosmology in the game has to be low. The upper bound is like 30 TeV. And of course, if you believe me, this is the way to explain, to motivate a new collider. Because LHC, as you know very well, cannot go there,
Okay, thank you very much for the talk, and thanks again to Pavel.